Hi everybody and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective, and this is lecture number 18 and the topic of the lecture is SPICE subcircuit model. So, in our previous lecture we had actually seen the basic idea of a SPICE and how does it recall the model functions and try to simulate it. Now, the types of devices that can be simulated on this platform are resistors, capacitors and inductors, which are passive element, and active elements will be diodes, bipolar transistors and MOSFETs. Even transmission line and power sources are being used as simulated ones, right. All the devices or even passive components can be divided into either linear or a non-linear component. For example, a resistor is a linear component, because if you plot I versus V for a current versus voltage characteristics for a resistor, it will always be a straight line, right. And that is the reason formulating a resistor component or its model will be relatively easy. So, what you will get in a resistor model file typically will be that for a fixed value, let us suppose this is this is the current versus voltage. Then if you plot the slope, then 1 by slope will give you the value of your R, right, because the slope will be given as del I and del V. So, slope of this graph will be del I del V, del I del V, and therefore 1 by slope will give you the value of your R, right. So, resistance will be there. However, you see the where does the complexity comes into picture is that let us suppose this is at T equals to T1, right, at temperature T1. Let us suppose at T2 it becomes something like this, and at T3 it becomes further like this. Then as the temperature increases, as you can see, the resistance actually starts to fall down because slope actually goes on increasing, right, and the same amount of voltage you get a higher current. So, you see therefore, though a resistor to general area is that it is always constant, yes it is constant for a fixed temperature, but as you vary the temperature it will be a function of the temperature resistance. How much is it so will depend upon the type of resistance you take and the type of the conditions you have. Similarly, you will have the capacitor and inductors. So, if you remember, capacitor charging and discharging shows a graph like this. If this is charging and this is discharging. So, this is an exponentially rising function and this is an exponentially falling function, right. Now, this exponentially rising and falling has been determined by basic idea of a capacitor. You can do that very easily from first principles. But these capacitor, depending upon the type of the capacitor, the charging and discharging rates will be different. So, this will be for example e to the power minus t by RC, right. So, RC is an external resistive network. Now, if a capacitor is connected to an RC network, let us suppose a capacitor is connected, how fast it is falling down, right, how the capacitor is behaving will be given by the model devices here. Active devices I discussed already with you, MOSFETs, bipolar transistors, which is BJT, and you have diodes, and transmission line and power supplies are of course part and parcel of these devices. Let me come to each the method of analysis. So, we have learned about the devices itself, which are active and passive. Their model files can be generated either through empirical models or through analytical models, and these are known as SPICE models. Now, we come to a point where we try to emulate the analysis method. What is the analysis method, right? What is the method for analysis? Analysis is a DC analysis, where we use all DC characteristics. Let us look at this DC MOSFET characteristics. I have this MOSFET here, right, given by some value, and I have this DC bias. This is the VDS or drain to source voltage, and this is VGS, gate to source voltage, and I have a, let us say, current meter where I am measuring the current, right. Now, what I do is I go on shifting the value of VDS from 0 to 0.5 to 1 to 1.5. So, my VDS values, right, for a fixed value of VGS, right, let us assume that my VDS varies from 0 to say 5 volts at a step of 0.5 volts. So, I will get what 0, 0.5, 1, 1.5, 2 and so on and so forth till 5 volts. Then for each value of voltage, say VGS is fixed at 2 volts, which is greater than the threshold voltage of the device. So, let us assume the device is in saturation. Then for each set of VG VDS pair, a current will be formulated. So, when you have VGS equals to 2 and VDS equals to 0, that will be the first point which is here. Of course, since VDS equals to 0, I will never expect to have a current in normal conditions, right. There will be some current which is primarily leakage current. At this stage, let us not go into that. Assuming that it is an ideal MOSFET and your drain voltage is effectively equals to 0, this would imply that the current flowing through that will be approximately equals to 0, and that is the reason you see exactly it is a 0 analysis. Now, let us come to the second point when VGS equals to 2 and VDS equals to 0.5. Please understand how will the SPICE understand that this is in non-saturated, because if you remember, the saturated condition was that VDS should be greater than VGS minus VTH. So, if your VGS is 2 volt, and since this MOSFET's name has been extracted, this name will have threshold voltage as one of the model parameters. So, what it will do automatically is that internally that it will subtract threshold voltage. Let us suppose threshold voltage is 0.5, then it will come out to be 1.5. So, any VDS value greater than 1.5 will be assumed to be in saturated condition. Anything less than that will be considered in the linear region. So, what it will do? It will try to find out the value of VDS 0.5, it is less than 1.5, and therefore, it is basically the value is basically in the linear region of operation, and therefore, the linear equation, right, from the model file will be extracted to calculate the value of current, and the current will be plotted here in this region, right. This is for various values of VGS we are trying to plot down. This is for a very low value of VGS. As the VGS value goes on increasing, the current value goes on increasing, right. And so, this is how a DC analysis can be done. We are still not doing any AC analysis, we are just doing a DC analysis here, and in the DC analysis what we are proposing is that the gate voltage is fixed and we are varying the drain voltage. Once we have swept the drain voltage from 0 to 5, we again change the value of VGS to 2.5, let us suppose, and then we do the same procedure. But please understand, when you make it VGS 2.5, your VD sat changes to 2 volts. So, what happens to your IV characteristics, which was actually starting from here, the saturation will start from here, right. So, this is your VSAT here and this is your VSAT. So, as the value of VGS goes on increasing on this direction, the VD SAT value also tends to increase. This is current versus voltage, right. And this is the basic idea behind the DC analysis of the SPICE model of which you see here. Let us now come to the AC analysis. AC will have, obviously, as I told to you, will obviously have the frequency as the changing factor or the variable parameter, and obviously the peak to peak voltage of the input signal will also be a variable parameter. And as I change the frequency, let me see how does the gain changes, let me see how the phase changes. That is what is done in the AC analysis. As it is written here, analysis of frequency characteristics looks into capacitance, it looks into gain, it also looks into phase. So, the left hand side is a circuit, do not worry from where the circuit has been taken or what is that. It is basically an analysis, AC analysis, and if you see what we have done is we have in the top figure we have plotted the gain value, right, with respect to frequency, and in the bottom figure we have actually plotted the phase with respect to frequency. Why this is important? Those who are aware of basic circuit analysis, extraction of phase is important to understand the stability of the circuit at that particular frequency, right. There are certain convergence rules and there are certain rules which will determine whether the device is stable or not. So, the whole idea is a priori, even before the actual characterization of the device starts, you are able to predict a priori for which range of the circuit will have stable and an unstable region of behavior. And that is the reason AC analysis is quite important and gives you a very good idea. However, here we are assuming, again as I told you in the previous slide as well, here we are assuming that it's an ideal conditions are being followed, there are no offsets available and there are no other issues coming into picture, and therefore we assume that they are perfectly ideal in nature, right. So that gives you a gain versus frequency. The first one is a gain versus frequency, and the lower one is phase versus frequency, right. And typically the frequency scale is typically in the log scale, which you will see, because obviously you can understand the frequency varies from right from hertz to maybe gigahertz. So you have ordered changes taking place here, and that's the reason your design or your x axis is basically a logarithmic axis in most of the AC analysis which SPICE does. Now what it does is basically it tries to sample the signal. I will come to that later on, but brief idea here that the AC signal is basically a time varying signal, right. It is a time varying signal which you see it is a time varying signal. At every point of time the values will be different, right. So what does AC analysis does is that it tries to say that minimum between these 2 points I will not measure, anything above than that we will measure, so that the number of points can be restricted without losing large amount of information, right. And this is how you do it, because otherwise it will take infinitely long amount of time in order to extract these values of gain and phase plots with respect to signal. Let me come to transient analysis. This is the third form of analysis, where, as I discussed with you, what I have done is I have given a signal which is something like this. This is the input signal I have given, and so they say, let us suppose this is my input signal. So every time my signal goes high, I have a high transition and I have a low transition at the trailing edge of this clock. Then when it rises high or falls low, how does it influence the output characteristics is basically known as the time response analysis for this case. As you can see, as it goes high suddenly, the output voltage goes to a very high value, there is a sort of ringing phenomena, and then it again goes down to the bottom, and then there is a ringing phenomena, and then so on and so forth. Basically that is what is happening here. So what will happen is that as it goes up, let us suppose the voltage goes up here, there is a ringing phenomena, then comes down here, and then there is a ringing phenomena, and so on and so forth, right. This is what happens, and this is the reason why there is a ringing phenomena. We will not go into details of that at this early stage of analysis, but you should know what is the transient analysis. Transient analysis therefore is the case when as t tends to 0, input signal goes from low to high, you are able to extract the value of the output signal, which might be a voltage or a current. Okay. There are other methodologies which people have used, and especially these are used for circuit simulation purposes. Now you could appreciate one important point. Let us suppose I have a MOSFET being used. Now this MOSFET is basically a 4 terminal device assuming source, drain, gate, the channel length and width, and there are doping concentrations and so on and so forth. Now what happens in reality is, when you take this MOSFET and use it in a circuit, there might be variations in the circuit elements. Say for example, there might be a variation in the doping concentration in the source and drain region of the MOSFET, right. And why is it so? Because no two fabrication processes can be exactly the same. There might be some variation in the process, because of which the circuits element variation will take place, and this affects your simulation. Monte Carlo simulations are all statistical simulations, right, and they have been used for quite a long time, where what you do, you take an ensemble of events, large ensemble of the same device, and then you vary the inputs and try to take an average value across the board, and then you say that if this is true, then I would assume that the output simulations will be correct, right. So the general term used for method in which random numbers are employed in simulation, and we do a numerical simulation taking into consideration this component variation. So let us take a diode and say that diode doping concentration is say 10 to the power 18, let us say 1 into 10 to the power 18, somebody comes to it is 1.5 into 10 to the power 18. Then what do? You run a Monte Carlo simulations with various diodes and try to figure out a single value of element, and then you say that okay, maybe this might happen that the most of the devices will fall in that big region where you have 1.5, which is the nominal value of doping concentration, and there will be some device which will be outlier. So if you plot, it will be something like this, a Gaussian function you will get. So these will be the outliers here with large deviation from the mean value which you get here, right. So sorry, this is the mean value and this is the mean value which you will get here, and there will be some sigma values, FWHM values across the network. full width at half maxima. As a result, Monte Carlo therefore gives you reflects onto the simulation platform the variations in the circuit elements, right. And in Monte Carlo simulations, the simulations that reflect the variation in different circuit elements, they are executed multiple number of times, and then the overall variation in the characteristics is evaluated. So, Monte Carlo obviously takes larger amount of time because the simulation time is larger, but it also uses large amount of CPU resources in order to do it, right. And the time for convergence in Monte Carlo is also very large. The third point of Monte Carlo is that you require very large amount of database in order to justify the Monte Carlo simulation. If there are say just 4 variations, then it will not give you a proper Gaussian output. But if you have 10,000 points, ensemble points where you are doing it, you will obviously get a very good natured Monte Carlo output simulation you will get. So, when circuit designers use EDA tools, they invariably run Monte Carlo variations and try to formulate the output characteristics of the device. There are 3 major sort of analysis methods apart from DC, AC and transient, that is the methodology of doing it. But if you want to do a high frequency analysis where your input frequencies are very large, then if you remember my previous talk also we have discussed that XC or XL, which is the inductive and the capacitive XL, this is the inductive and capacitive reactances, they will vary with omega. So, as the omega becomes larger and larger, XC starts to fall down and XL starts to become large and vice versa. So, typically we use in SPICE S parameter modeling for high frequency characteristics analysis. When we basically S parameter has got 4 parameters S11, S12, S21. So, I get S11, S12, S21 and S22. These are basic parameters. I will not go into details of these parameters, but once you are able to extract these parameters for a high frequency model, you can pretty well get the variations in the currents and voltages for high frequency modeling. And I am assuming in this case that the high frequency is so high that your device is able to respond to those high frequency changes which is happening. Let me come to Fourier analysis, and this is basically a signal distortion analysis and a high frequency domain. And finally, noise analysis, which is basically a measurement of the electrical noise in a circuit, right. And these are very important when you do basic analog at very high frequency and you do not want your signal to noise ratios to go down below a critical value. You need to find out the noise, and how noise varies with frequency is very important when you do a noise analysis methods. Now, SPICE was actually a free simulator. So, Linear Technology is a company where SPICE is a free simulator. You can get it online and you can download it from Linear Technologies. This is known as LT SPICE, right, Linear Technology SPICE, and it is quite similar to P SPICE, which is, but the number of nodes and devices are not fixed to a larger extent. They are fixed, and most of the industry analog digital circuits use LT SPICE for that purposes. And Linear Technology is a company which gives you the complete set of SPICE model for LT components, for linear technology components. So, you have Linear Technology, which is a company which provides you with large number of device models for these components in this case, right, and they give you a large component available to you. SPICE Lite 9.2 is from the ORCAD family of products, and they offer a complete suite of electronic design automation tools. It is free, and P SPICE can be used for analog circuit simulation. P SPICE A/D, which is ADC actually, data converters, can be used for mixed signal analog and digital circuit simulations. Typically, P SPICE node 9.2 is typically limited to approximately 64 nodes, 10 transistors and 2 op amps and 65 primitive digital devices. These are just numbers, right. You need to actually do this in order to appreciate the output characteristics of the device, right. Let me come to 2 important points before I close this lecture. The first is the convergence property. So, what happens is that whenever you are told to solve a circuit, right, using nodal analysis, you do it using matrix manipulation, right. All of you know possibly this particular point. Let us say for example, you want to find out current voltage, then you do it a matrix form. In the matrix form, you get the value of the voltages, do a transpose method and try to extract the value of the current. Now, many a times internally, if you have a differential equation and we need to solve it, the methodology used to solve a differential equation is a Newton method, typically also referred to as a Newton-Raphson's method or NR technique, and they are used for first order functions, right. What it does, I have a differential equation, I choose a trial function, right, and then put the trial function into the method, into the Newton-Raphson technique, and I see if the solution is diverging beyond a point, I say that my initial assumption was wrong, right. So, this is basically iterative process, and depending on the previous output, the next input will be chosen. Just to show an example, look at the bottom these figures here, this one and this one. The left one is basically a simple diode, right, and the right one is, let us suppose, a complicated sum device, right. So, if you look at the left diode, then this is my IV characteristics of the diode, current versus voltage, which is given by exponential QV by KT minus 1, something like this, IS, and so on and so forth. This is current. And where the load line cuts the graph, that is the quiescent point, which you know, which means that if you want the diode to give you a proper output, then it is always advisable that the point where the load line is cutting the IV characteristics is the quiescent point. Who determines the load line? It determined by the external circuits. What are the external circuit? This is the voltage and the resistance, right. And who gives you the internal case? This IV is given by the diode itself. Where they cut, that is the point where both the currents will be equal, and I can sufficiently say that these are equal. So, let us take this blue curve, blue point to be the initial point. In the initial point we say like this, so its corresponding current will be, which is high here. I know this is larger than this, so what I do is I go down from here to this particular point to a lower value, and similarly I go like this and then I go like this. So, this is basically an iterative approach which we are trying to do, and we are trying to reach to the operating point here finally. So, within 3 to 4 steps I am able to reach the operating point. Whereas, if you look at the right hand side, a relatively more nonlinear complicated output characteristics, it takes multiple times before your convergence is there, and therefore, there might be a convergence error happening to you, that you will never be able to converge to this red dot. This red dot is the point where we need to come, but because of the nature of the graph, I will never be able to approach the red dot in any case. Once this happens, I end up having a large convergence error with me. So, this is one major problem, stability problem, convergence problem with SPICE simulations. One more problem is the right hand side shows you a simulation, right, and the left hand shows you the actual data sheet of a diode. This is the forward characteristics of a diode you can take, this is the forward current versus the voltage which you see, right, for various temperature. As you can see, the data sheet on the left gives you the accurate values of the current, and what does the right gives you? The emulated simulation of the data sheet. So, you see they are so smooth, it does not actually match with the data sheet of this one. So, this is an approximation which people do. However, the variation is so small that I can afford to assume that the simulation is very close to the data sheet. So, the cost I am paying for it is that slight difference in the accuracy, but the speed of simulation is very high, the convergence is also very high, right. Now, if I have an irregular characteristics which is on the left hand side, as you can see, then any equation, right, will not be able to do 100% justification of overlapping this irregular expression with a mathematical expression, right. So, if you let us look at the same expression which I was always discussing with you, that the forward current is given by reverse saturated current, right, IRS into exponential Q times V divided by KT minus 1, let us suppose I write down. So, as the value of V increases on the, so since it is a log scale, you see it saturating, but if you plot IV as we know of it in a device, it will be something like this. So, as the exponential voltage goes on increasing, right, the current goes on increasing, fine. But let us suppose it shows something like this, and then shows a deviation and then it goes like this, then this deviation will not be handled or captured by the model file, right, and there might be few small error in that particular domain, correct. With this basic idea we will end today's class, but I will give you the brief recapitulation what we did today. We discussed with you the basic idea of types of analysis. So, DC analysis, AC analysis and transient analysis, and then we looked into the various simulation tools, like for example, when we do a noise analysis, Fourier analysis, and we looked into the other one. We also went into the fact that I can use a Newton-Raphson technique for solving any differential equation, but it is an iterative process. So, more complex or output the device is, relatively more difficult for the Newton-Raphson technique to converge to its actual value. And finally, we saw that if your device output characteristics experimentally determines highly irregular in nature, no mathematical tool will be able to emulate it 100% accurately. So, we forego that much amount of slight error and we say that our output characteristics is fast in terms of fast convergence rates, right. So, this was what we have discussed in the SPICE simulation, at least in this case. When we meet next time, we will be discussing with you how to load a SPICE model, right. You should also be aware of that, how you should be able to load it on your laptop or a computer and try to solve some basic equations in the analysis. So, with this let me stop today's lecture. Thank you very much.